In this video, we are continuing our series exploring how statistics can be useful for understanding issues of sustainable development. Today we will look at the topic of hypothesis testing. Some terms that you will come across in this video are the null hypothesis, the alternative hypothesis, and type 1 and type 2 errors. In my last video we looked at the normal distribution and saw that the height for age of healthy, well-nourished children under 5 follows this normal distribution. The height for age of the median child among the healthy population is given a standardized Z-score of 0, and all our other children are distributed according to how many standard deviations the height for age is above or below the median. Suppose now that there is another hypothetical population of children that are not healthy and well-nourished. If we were to measure their height for age, what would that distribution look like? It might be reasonable to assume that this population is also normally distributed. Due to genetics and other environmental factors, we would expect there to be a lot of diversity of heights among these malnourished children in the same way that we saw this diversity among the healthy children. However, we would not expect this malnourished population to have the same median as the healthy population. We know from nutritionists that chronic malnourishment is one of the leading causes of stunting in infants, so everything else being equal, we would expect a malnourished child to have a lower height for age than a healthy child. Let's now superimpose our bell curve of malnourished children on our bell curve of healthy children. We would expect the distribution of malnourished children to be somewhere over here, to the left of the healthy distribution. The pink crosses denote our healthy children and the purple crosses are our undernourished children. But notice something interesting. These two distributions overlap. Because both populations are normally distributed, there are always going to be some healthy children that have a height for age lower than some malnourished children. So if all we can observe about a child is the height for age, how do we know whether or not that child is actually suffering from stunting? This is where hypothesis testing comes in. To understand the concept of a hypothesis test, let's think about a court of law. How does the jury decide whether the defendant is guilty or not guilty? They generally don't know for sure whether the defendant actually committed the crime or not, but rather have to come up with their best judgment based on the evidence available. We tend to follow the premise that people are innocent until proven guilty. Statisticians call this the null hypothesis. We start with the hypothesis that the defendant is not guilty, and then test to see whether there's sufficient evidence to reject this null hypothesis in favor of some alternative hypothesis that they are guilty. Of course, this process is prone to error. If the jury is too quick to deliver a guilty verdict, there is a risk that an innocent person might be sent to jail. Statisticians call this a type 1 error, the error that results from incorrectly rejecting the null hypothesis. On the other hand, if the jury requires absolute proof of guilt before delivering a guilty verdict, this risks that a guilty person may be let off. This is a type 2 error, the error that results from failing to reject the null hypothesis when we should have done so. So let's recap the key terms. The null hypothesis is the starting assumption, which we take to be true if we have no evidence to the contrary. The alternative hypothesis is the new truth, which we are prepared to accept if we have sufficient evidence to reject the null hypothesis. A type 1 error results from incorrectly rejecting the null hypothesis, and a type 2 error arises from incorrectly failing to reject the null hypothesis. Statisticians, just like a legal jury, want to do the best they can to avoid both types of error. Let's now take this model out of the courtroom and apply it to the issue of stunting. If we take a child and all we know about that child is the height for age Z-score, how do we decide whether or not that child is stunted? How do we test the null hypothesis that the child is healthy and not stunted against an alternative hypothesis that the child is stunted? In other words, how do we decide whether the child is one of the red crosses and comes from the distribution of healthy children, or is one of the purple crosses and comes from the distribution of malnourished children? To do this, let's use some real-life data. The dataset I'll be using comes from the Young Lives Study, a project by the University of Oxford that follows the lives of 12,000 children in Ethiopia, India, Peru, and Vietnam. Specifically, I'll be using a dataset containing information on a sample of 1,906 babies between the ages of 6 months and 17 months living in Ethiopia in 2002. For each child, we know their height for age Z-score. Let's take one child in our sample, whom we will call Mohammed. Of course, our data is anonymized, So we don't know the real names or identities of any of the children or families, but we do know that Mohammed is a boy aged 14 months and living in Addis Ababa, the capital of Ethiopia. He has a height for age score of minus 0.95. In other words, his height for age is 0.95 standard deviations below the median for healthy children. That puts him about here on our normal distribution diagram. Does this mean we should accept the null hypothesis that he is in the population of healthy children and just happens to be a little bit small for his age? Or do we reject the null hypothesis and say that he is likely to come from the population of malnourished children? Let's now take another child whom we call Mariam. We know that Mariam is a girl aged 15 months living in the Amhara region. Her height for age Z-score is minus 2.13, putting her here on the normal distribution. She's clearly less likely to come from the healthy population and more likely to come from the malnourished population than Mohammed. But is she sufficiently far enough to the left for us to reject the null hypothesis that she is a healthy and well-nourished child? Indeed, where is the cutoff? In this case, fortunately, the UN has made that decision for us. Recall the Sustainable Development Goals, Target 2.21, from the last video. A child is classified as stunted if they have height for age of less than 2 standard deviations below the WHO growth standards median. In other words, we should reject the null hypothesis that a given child is healthy if they have a Z-score of minus 2 or below. Recall that the normal distribution tells us that 2.5% of healthy children will fall below this threshold. So the UN's definition of stunting will incorrectly classify 2.5% of healthy children as being stunted. For these children, type 1 error has been made, equivalent to finding an innocent person guilty. However, if the cutoff was moved further to the left, to reduce the probability of making a type 1 error, we would then increase our chances of making a type 2 error, that is, classifying a child as healthy when in fact they are malnourished. As our malnourished population is hypothetical, we don't know the exact position of this distribution in relation to our healthy population. So we can't actually put a figure on the size of this type 2 error. So, based on this cutoff of minus 2, we do not reject the null hypothesis for Mohammed as he has a Z-score of minus 0.95, which is closer to the median than the minus 2 cutoff, so we are prepared to accept that he probably comes from the healthy population. But we do reject the null hypothesis for Mariam because her Z-score of minus 2.13 is beyond this minus 2 cutoff, making the judgment that she is more likely to come from the malnourished population. When we do this test for every child in our Ethiopian sample, we find that 31% of them have a Z-score of less than minus 2 and so are classified as stunted. So what have we learnt today? Hypothesis testing is a useful way of framing research questions. In the height for age data, our null hypothesis or starting assumption is that a given child comes from the distribution of healthy children. We test this against an alternative hypothesis that the child comes from some other distribution, in this case the distribution of malnourished children. To make our decision, we must compare the child's height for age Z-score with some cutoff point. The UN has selected a cutoff point of minus 2, and in fact that is a conventional cutoff point for many statistical applications. Choosing this cutoff point of minus 2 means that we have a 2.5% probability of making a type 1 error, meaning that 2.5% of children who are actually healthy will be misclassified as malnourished. Thank you for watching. Next time I will show how the concept of hypothesis testing can be extended to allow us to say more about our sample of Ethiopian children as a whole.